Hi, good evening to all. So we'll wait for 2 more minutes. We can start at the 5:10. Okay. So sorry for the delay. Yeah. So once again, good evening. So last class we started with the trees, right? So I'll just give a revision. So first of all, we saw what is a tree and how the nodes are related. Okay. So the topmost node is called the root node, and the bottommost nodes are called leaf nodes, and then we have the intermediate nodes. Okay. And we classify the tree based on the maximum number of children it has. Okay, a binary tree is a tree which has at most two children. Okay, at most listen, like it will have either zero children, one child, or two children. Okay, and I told you that we'll be dealing only with binary trees. Okay, and then next tree which we saw was a full tree. So full tree is a tree which has all the nodes except the leaf nodes having two children. Okay, so it is just a concept. There is no implementation for a full tree. Okay, it is just a concept. Full tree means all the nodes except the leaf node will have two children. That's it. Okay. Next is a complete binary tree. So we saw what is a complete binary tree. The only property for a complete binary tree is the nodes will get filled from left to right. Okay. And then we saw what is the application of complete binary tree. Okay. So in a complete binary tree, the nodes or the data which you're going to insert are completely random. Okay. They don't follow any property and all. Okay. So now, because of that, what happens is, so why actually it's a non-linear data structure? Non-linear means it takes a branch. So why we are going for a non-linear data structure is to reduce the search complexity or the retrieval complexity, right? So if again the data are random and it is stored in a linear structure, then what happens? Again, the complexity is not going to be reduced, right? Okay. So to avoid that, we are going to impose some property, and that property is a binary search tree. So for a binary search tree, we have the left nodes data will be less than the parent nodes data, and then the right nodes data will be greater than the parent nodes data. And that particular property will be followed for each and every node. Okay. And so we also saw how a complete binary is implemented in a list. Okay, so we saw the parent child property, right? So how we find out the left child using the parent's index and the right child using the parent index, like that we saw. Fine. And then we came for an implementation of binary search tree, and we saw a sample of insertion in a binary search tree. Okay, and then we tried implementing it. Okay, we started implementing it. First, we need to create a node. In the node, we have three elements. One is the data part, left link, and the right link. Okay, every node you can see we have a left node, sorry, left link and the right link and the data part. Okay, and so we are initializing with none. Why? Because if a new node is inserted, that is going to be the leaf node. Okay, the property of a leaf node is both left link and right link are none. Okay, that's the reason I give default values for left link and right link as none. Okay, this is the node class. Now coming to the tree class, BST tree, binary search tree. Okay, in binary search tree, we know we'll have only one parameter, which is a root, and this root is going to store the address of the root node. Okay, it is going to point to the root node. Okay, so we have the root value, and that will be pointing to the root node, and yeah, you can see over here. Okay, root will be pointing to the first node. And then the insert function. Okay, in the insert function, we saw how the node, a new node is being created, how it is filled, and then how it is linked to the existing tree. Okay, so creation and filling happens in the single step. Okay, a new node, okay, of data. So if you pass data, what happens in the node? Data will get assigned. Left link and right link will be assigned as none. So that is what we need, right? So a node will be created. Okay, and then the left and right will become none. And we put a separate condition to for the scenario where the head value changes. Okay, so sorry, not head value, root value. So here the root value changes only when the root is none. That is, the tree is empty. Okay, so we check whether the tree is empty and then directly assign the new node to root. So this is the if condition. And the else part, what we do is we search for the location where to insert. Okay, where will we insert? Only if we reach none. Okay, at that position we will insert. So for that, I am using a while loop and a temporary variable for iteration. Okay, I cannot use root for iterating, right? Okay, because here also tree is irreversible. We cannot, once moving forward, we cannot go back. Okay, so now what happens is while loop. Okay, the while loop, once it comes out of the while loop, the temp value would be none, because that is the condition, right? Till temp value becomes none, I need to keep on iterating. Once it reaches none, I will come out of the while loop. But there is no use in having none in temp. I cannot modify, okay, or I cannot add using none, right? So for that purpose, what we are doing is we are using one more variable called previous, which keeps it is like taking a backup of temp before changing it. Okay, so it will just store the temp value before updating the temp value. So once it comes out of the while loop, temp would be none, whereas previous would be pointing to the last node. And this if condition, why we are doing this if condition is we have the last node's data, but again we need to find out whether to insert the new node to the left hand side or the right hand side. For that purpose, we put one more condition: data. If data is less than previous, insert it to the left of previous, else insert to the right of previous. So this is the third function. And then you have the in order traversal. Okay, so in order traversal means first we are moving to the left, and then we are printing, and then we are moving to the right side. So like this, we saw three traversals and saw the output also: in order, pre-order, and post-order. Just interchange these print statement and the left and right traversal. You will be able to get the output of pre-order and post-order also. Okay. And next we saw search. Okay. So for searching, again we use the property of the binary search tree. So we need not go and search for the entire tree whether the element is found or not. So since it is following a binary search tree property, either we move to the left or right based on the data and the current node's data. That is the key and the current node's data. If the key is less than the current node's data, we just go to the left, skipping all the right side of that particular node. Similarly, we like do it till we reach the element. Okay, till we reach the key. So if the key is not found. So when will you know that the key is not found? When the root reaches none. Okay, the root reaches none, you can say that the key is not found, and then you can simply return. That's it. And then we saw on some more additional functions, like one of the function was count. Okay, so the basic idea of count is, if you are in a current valid node, that is a non-null node, then I have one count. Okay, that is why this one over here. And then the left recursive call will take care of counting the number of nodes in the left hand side. And then the right recursive call will, like uh, you will count the number of nodes in the right hand side and return back. So with respect to the current node, number of left nodes plus 1 plus number of right nodes will give the total count. That is a basic idea, right? So till this we saw. So any doubts, anyone? One second. Yeah. Any doubts?
No, sir.
Okay. Fine. So in the last class, I asked you to find out the logic for finding the height of the tree, right? So did anyone try it out? I even gave you the idea. Anyone? Yes. What is the answer? Can we tell the logic? Okay. So if root is equal to none,
Root
this
is
is,
equal, return 0,
yeah, return 0,
else
else
left height is equal to,
return.
mm, sir, I have increased the steps actually. I have written first
Okay. Okay.
left height, L
Left
height,
height. Okay. Is equal to.
BST dot height, bracket root dot LL.
Okay.
Mm,
And then
and then RH
RH is equal to
BST dot height root dot RL.
height of root dot RL.
Uh, and then I have written height is equal to LH plus RH. Sir,
No,
I'm not sure whether it will be just adding or
no,
plus
no.
one will be there or not.
Plus 1 should be there, but actually it is not just adding, right?
Okay.
See, you can take this example. Okay, let us take this entire tree itself. Okay.
Mm.
So for respect to 50,
Yes, sir.
height of left subtree is 3,
Mm.
height of right subtree is 1, 2, 3, 4.
Mm.
So 3 plus 4 is 7, right?
Yes, sir.
But actual height is only 5.
Okay. Okay, okay, yes.
So I told you that it is nothing but the maximum of heights of left and right plus 1.
Okay, whichever is higher.
Yeah. So
Okay.
left is 3, right is 4, right? You should take
That means
4 plus 1,
plus 1, 5. Yes.
5. Okay.
That means we have to apply if condition also, no?
Yeah, either you can apply if condition or you can write a max function separately and then you can call that.
Okay.
Yeah, we can write if condition. So I'll also tell you how to write a ternary operation. Okay, so um, L H if uh, LH greater than RH. This is one type of statement. If else in a single line, okay? Else RH. Return H plus 1. And height is equal to ST dot. Four. Okay, for this tree it is 4 only. So 50, 30, 75, 45, 90. So for this tree, the height is 4. Okay, 50, left is 30,
45 also.
45, the right of 30, and 75 right side. But the height is 3 only, no? Why 4? Just okay, 80 is also inside, right? Okay, this is 80. 75, 50 right side 75. Again, right side 90. Right of 75, 90. And then 80 to the left of 90. So that'll be right side is 3, right? So 75, 90, 85, 80. So plus 1. So 24. Able to visualize, right?
No, sir.
Okay, I tell you. So first was 50, then 30, then 75,
Right side.
and then 45.
45 right of 30.
Yeah. Then 90, and then 80. Okay. Now the height is 4.
1, 2, 3, 4. Yes.
Yeah. So height is 4. Fine. So now let us go to the next like subtopic in trees. This is deletion of an element. Okay. So for deletion of an element, you need to understand. Okay. Like so how deletion happens is there are three different types of nodes actually here. Okay. So one node is deleting a leaf node. Okay. Just a minute. Yeah. So actually, if you see here, there are three different types of nodes. Okay. One is leaf node. Okay. With that is a node having no children. Okay. Another is like a node which is having one child, right? So you have 5, 75, 90, 80. All these are having one child. And other type of node is node having two children. Okay. 30, 50. Okay. Three different types of nodes are there. Okay. So we need to understand what to do for these three different types of nodes. Okay. So first of all, how will you classify what under what class it comes, whether it's a zero child, one child, or two child? How will you write the conditions for that? How will you check whether it's a leaf node or child with no children. Sorry, node with no children.
So if root is none,
No, root is none means tree is itself empty, right?
yes, yes.
Zero children. One child, two children. So what is the property of 10? And what's the property of 85? So 10 and 85 are not having any children, right? No child nodes are there. So what does it mean? I mean, like, so what is the, can you see the property?
The
And
left,
even 45.
left and right both are none.
Yeah, that's it. Okay, so it is, these are actually leaf nodes, right? Left and right, both none. Okay, for zero child node. For one child,
Any one will be none.
Either left or right would be none.
yeah. So here and here it would be or. Okay, L, left or right is none. And for two children,
Both are not none.
both are not none. But actually, there are only three classes, right? We not write a separate condition. This will come in the else part.
Else part,
Okay,
yeah.
if, else if, and this is else. That's it. Okay. Fine. So now we know how to classify a particular node. Okay. Now, so actually, like what happens if we remove a zero child node? So if we remove 10, so where is the change happening and what is the change?
The right side of 5 will become none.
Yeah. So how is 5 related to 10?
5 is the root node of 10.
Not root, parent.
Sorry, parent. Parent.
Yeah. So 5 is the parent of 10. So actually the change is happening in the parent node. Okay.
Hmm.
So like we need to somehow keep track of the parent. So we know the node that we're going to delete is 10 and its parent also has to be kept track of. So like what logic can we use to keep track of the parent?
We can check if the parents left or right becomes none.
No, no, no. See, my data that I'm going to delete is 10. Suppose that I reach 10. So I want its parent also. Suppose I use the search algorithm to find 10 and then I somehow got the address of 10. I
The
want its
temp,
parent's address also.
the temp variable which we used,
Yeah, that is the 10. That is 10.
and another variable which you use to store the value of temp before changing it.
Yeah, very good. So in insert function, we use the same logic. Like we store the previous before changing the temp value, right? You can apply the same logic to do that. Okay, so if previous is, so we can keep track of the parent using the previous variable. That's it. Okay, so suppose like using that logic, we have the parent and we have x. X is the node that you're going to delete, and we have p, which is the parent node of x. Okay, suppose that we have these both these nodes. Now tell me what change will happen if it's a leaf node deletion. There is zero child node deletion. What condition we have to put and x, which is a node to be deleted. So we need to check to which side x is connected to parent, right? And the corresponding link has to be made as none. Understood? Are you able to follow? See, suppose if I delete this node 10, what will happen to 5? 5's right side will become none. If I make this none, it means 10 is being deleted from the tree, right? Okay. So now what we're doing is we know what is P and what is X. So we're just going to like check to which side 10 is attached to P, and then the corresponding link is made as none. I just write the logic here. So if so, can you tell the logic? Anyone? Just check where is X linked with the P, whether the left side or right side. Using what we can check. So here X is attached to the right. No.
Data.
Hello. Yeah, using data. So what is the condition? Tell me as a condition. If
X dot that X X is greater than parent.
no, X is a node. X dot
Okay.
data. Okay.
X dot data
Okay. X dot data.
greater than P
Hmm.
dot data.
Very good. If X dot data is greater than P dot data, what should I do?
P dot RL equal to 9.
Yes. P dot RL is equal to
Equal
none. Okay. So else we can make
left
P dot
hand
LL is equal
L
to none.
9.
That's all. So this would be your leaf node deletion. Okay. Node with 0 children deletion. Got it? Now let us come to node with a single child deletion. So like for example, I want to delete 90. Okay. So if I want to delete 90, tell me what all changes should happen. What will happen to the children of 90, or what will happen to the child of 90, because there is only one child, right? I know that 90 has only one child, single node linked to it. So what change will happen if I remove 90?
80 will become the parent.
80 will become the
Parent
Later,
node.
right
parent
side
node,
of
or
75.
yeah, correct. So we just change the link. Okay. So 75 was pointing to 90. Now we have to make 75 point to 80. That's all. Okay. How to do that? 75 was pointing to 90. I want 75 to point to 80. So what change should I do?
Through 90, we can get the address of 80, right?
Yeah, correct.
So we can directly change the address.
Yeah. So just take, okay, like first you have to check whether 90 is having left child or right child. Okay, take the corresponding link, which is not none, and then put it to the parents link, corresponding link, wherever 90 was attached to. So 90 was attached in the right hand side, and 90 is having a left child. So what you have to do? Take the left link of 90 and put it as the right link of 75. Understood? Okay. So we have to check whether like so again we have P and X. Okay, X is the child and P is the parent. So we have to check whether X is attached to the left side or right side. And second thing is one more check you have to do, whether X is having left child or right child. Okay, fine. So first is we need to check where X is attached, whether it is attached to okay left side or right side. After that we have to check where this X is, sorry, uh, which child X is having, either left child or right child. Understood? Okay. Can you tell me as a statement? First, we need to check to which side X is attached to P. Same condition, right? If so, did you get it or any doubts? So if x dot data is greater than p dot data, so if this condition is satisfied, it means that x is attached to the right hand side of p, right? So x is attached to the right hand side of p. Now again I have to check whether x is having a left child or right child. So how to check that? Can anyone tell me? What's the condition I need to put?
You have to check if it is none.
None. If x dot RL,
If it is none or not none?
If it is none, then no left or right child is present.
No. I already know that 90 is a one child node. No,
Then
I
you
want
have
to
to check
know which
which side.
side.
Yeah, then which side is not none.
Yeah, we have to check for not none. Okay. So if x dot L not equal to none, okay, it means that x is having a left child, right? So now what should I do? X is attached to the right side of P, and then x is having a left child. So what should I do? X is attached to the right side, and x is having a left child.
P dot RL equal to
P not RL is equal to x dot.
Yes, P dot RL is equal to x dot
LL.
LL. Nice. So else, so this else is for this if. Okay, which means that x is having a right child. Okay. Now what should I do? P dot
LL.
no. No, x is having the right child. Okay. X is attached to the right side of P, and then x is having a right child. Okay. So P dot RL only is equal to x dot RL. Okay. And now this else is for this if condition. X dot data greater than P dot data. Which means that if this comes to else part, which means x is attached to the left hand side of P. Okay, to the left hand side of P. So we can put the same condition, just need to change this RL to LL. P dot RL to P dot LL. That's it. Okay. Any doubts in leaf node deletion? That is zero children deletion and one child node deletion.
No, sir.
Understood, right? Okay. So now next is node with two children deletion. Okay, for that I require a larger tree. Okay, I'll just construct one more tree. Or do I have? Okay, I'll construct. Okay. So let us consider this tree. And now we're going to delete 70. Okay. So now, like in the previous two cases, like if I delete, there was only one link. So immediately we just shifted the link and then like we got the correct order. But whereas here, if I remove this, I have two subtrees, right? Left subtree is also there, right subtree is also there. Okay. So like, so the proper arrangement cannot be done if I directly remove the 70. So which will come first and again, which will be the, which will be linked to where, so all those confusions will be there. So to avoid all those, what we're going to do is we are going to find a substitute for this place from the right subtree. Understood? So we're going to make a substitute for this 70 from the right subtree, and then we can delete whatever you have substituted from the right subtree from here. Okay, that will become a dummy node, right? Suppose I'm taking some 73 or 90 and then putting it over here, that will become a dummy node because already I have 90, so I can remove that, right? So that is the basic idea. Now the question is, which is the correct node to replace 70 from the right subtree? Yes.
The smallest one.
Yeah. So is it 72?
72.
Yeah. So why the smallest one?
So the remaining elements will be on the right side. I don't know.
Yes. So we need to, like, even after doing a rearrangement, binary search tree property should hold, right? Okay, suppose if I take 80 and put it over here, and you have all other nodes like 75, 72, 73, these three nodes would be less than 80, where that is not possible, right? So right side, everything should be lesser. Even if I put 73, which is the leaf node. So if I put 73, we have one more element 72, which is less than 73. That is also not a binary search tree. So the correct node that has to be replaced is the smallest node. Okay, 72 is the smallest node, so I can replace it with 72 over here. But the next question is, how will I find the smallest node? So where is this
So
smallest node located? Yeah, tell me.
No, sir, it's okay.
Yeah, no, you can tell me. So where is this 72 located?
Left in the
Sorry,
left subtree.
left subtree. 72, 75 is also the left subtree only. 73 is also left subtree only.
left of 75.
No. Where is it look? I mean, like I want a general answer, not with respect to this tree. See, actually, the 72 is the leftmost node, right? It doesn't have any more left children. Okay, if at all it has a left child, then that would be the smallest node. Am I right? Suppose if there is one more node 71, which is the left side of 72, then that would be the smallest node, right? I would be replacing 71 with 70. Okay, so the
Yes,
smallest
yes.
node is the leftmost node of what?
Right.
The right subtree. Okay,
Right subtree.
for this right subtree, the leftmost node is what we have to replace with the corresponding node. So now what I do, I just replace the 71 with 70 with 71. And now this becomes a dummy node. Now deletion, either this would be a leaf node or a one child node. Definitely, right? Because it's a leftmost node. Either if it has a right child, then it's a one child node. If it doesn't have a right child, then it's a leaf node. So we already know how to delete a leaf node or a one child node. That's it. Okay. So for two children node deletion alone, there will be a substitution. And after that, we'll delete whatever node we have substituted. Okay. Fine. So the whatever logic I have told you, just keep this in mind and try to implement it. Okay. Now we'll see how to like solve this same problem using recursion. because if this is done using iteration, there'll be the length of the code will be much larger, because you have to write a lot of conditions, okay, and checkings and all have to be done. So if you write it using recursion, the code looks much smaller, and then only thing is you have to understand so how the flow is going. Okay, so I'll help you out in writing a recursive code, but you have to try writing a like iterative code, okay, without using recursion. Using loops you have to try to figure out how to delete a node. Okay, fine. Now let us see delete of root. Okay, so now like what is the negative condition? It's a recursion, right? So what is the negative condition, or is there any negative condition? Hello. Negative condition means like we are not able to delete an element. When will we not able to delete an element? So what would we pass for delete? Actually, you have to pass one more. You also need to pass key, right? The node, the data to be deleted. Yes, the negative condition is if the key is not present in the tree. Did you get it? See, it will be similar to search only. We are searching for a node, we are not able to find that node means uh, it's not present, right? Are you able to follow or not?
Yes,
Yes,
sir.
sir.
Okay. So if root is equal to none, you can print some warning messages. Print and then return none. Okay, so this delete is going to return a value. Okay, a value in the sense the address. See, for example, I'll just okay. So suppose if I delete 10, okay, earlier it was 10x only, right? So suppose if I delete 10, the value that has to be like replaced with the right side of 5 is none. So since it is recursion, what happens is only if I return some value from here, that will be replaced over here, right? So what I do is I will return some value from here that should replace here. So even for deleting this 90, so what I would do is I would return 80 from here. Okay, from this node, if I return 80, what happens? It would start pointing to this node. Got it? 75 will start pointing to 80. Right? So from this, what should I pass to the previous node? Because this is not the node to be deleted, right? So I should pass the same value itself. The root itself I have to pass. So that it will get replaced. No change will happen. But actually it is getting overwritten by the same value. Understood? So here I will pass 80x so that the will become 80x. Okay, so here I'll pass 75x itself so that there'll be no change at all. The same value will get overwritten back. Okay, so this is a basic idea. I'll finish the code and then I'll explain you again if you're not able to understand. So that is why I'm returning none. So if the element is not found, so I'll return none. Okay. So if you want to write else, you can write else, or you can just leave it because I would put a return here, right? So for safer side, let me write return. So now coming to the positive condition. Else if, so what is a positive condition?
equal to key.
Not root. Root is the address. Root dot,
Root dot data.
yeah, root dot data is equal to key. Okay, if root dot data is equal to key, now here only we are going to perform the deletion. Okay, as of now, let us leave it empty. Let us complete the traversal part and then we can come back to deletion. Because here only we are going to write if it's a leaf node what to do, single child node what to do, two children node what to do. All those logic will come over here. Okay. So else if, so when should I traverse to the left hand side? If key is less than
Less than 2.
root dot data. Okay, now what I would do is I just call the delete function. Okay, return bst dot delete of root dot left link comma key. So why I am putting a return over here? Why? Because see, this will return like okay. So from here I should return 75 to back over here, right? That's why. So actually it's not return. I'm sorry. So it is actually root dot left link is equal to. So if key is less than root dot data, the change will happen in the left side of um, change will happen in the left side of root, right? That is why. Are you able to follow? See, suppose if I'm deleting 5, okay, so now what happens? 30's left child will get deleted. So what I'm doing is, if I'm standing in the current node 30, so I'll write 30x dot left link equal to delete of 5. Okay, so I'll pass 5x and then I'll delete of 5. So now what happens? This will return 10x from here and then this will be replaced with 10x. So that is the basic idea. Able to follow? Yes.
Yes, sir.
Okay. Else root dot right link is equal to bst dot delete of root dot right link comma key. Okay, now the recursion part is over. Now coming to the logic. So now I have found out the key and this root is pointing to the node which I'm going to delete. Okay, suppose I'm going to delete 90. This was 90x, right? So now root is 90. 90x actually. I found out the data to be deleted. Now I am checking whether it is a leaf node. Okay, so what is the condition? If just now we discussed, right? Leaf
If
node.
the data is greater than p dot data, root
No,
dot
no, no,
data.
no, 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 no. I'm asking for a leaf node condition. That is zero children condition. See this one.
Yes, sir.
So both the links are
None.
none. Okay. So if root dot left link equal to none and root dot right link equal to none. Okay. So if both are none, what should I return? If it's a leaf node deletion. See, if I'm deleting 10, so what should I return to the previous recursive call?
None.
None. So if I return none, here this particular position, none will be replaced. Right? That's it. So return none. Understood? Okay. If, that is else if, instead of and I put an or. Okay, fine. So if I put an or, then again I have to check whether it's having left child, right child and all. So avoid that, I can just put a single condition. So what does this mean? If root dot ll equal to none, what does this mean? So this condition is false. And if this condition is true, what does it mean?
There is a right link.
There.
Yes, correct. See here, this is false means what? Both are not none. Okay, it means that both are not none means like left link and right link both are not none. There are two more possibilities. Any one of the link is not none, or both the links are not none. Two possibilities are there. Okay, so here I am checking whether left link is equal to none. If left link is equal to none, definitely right link is not equal to none. Okay, so now what should I do if right link is not equal to none?
Return root of 0 dot
Yes,
right link.
just return root dot right link. Okay, else if
Root dot RL equal
root dot RL is equal to none.
return root dot left link.
Yes, return root dot left link. That's all. Okay, this is single zero children, single child. These both are for single child addition. Okay, now coming to the else part. So what does this else mean?
Both are not none.
Both are not none, which is a two child deletion. Now we're going to write the logic for two children deletion. So for two children deletion, the first step what you have to do is you have to find out the substitute. Okay, which is the correct node that has to be substituted, right? So now, like, what happens here is we're just replacing this data part, right? We are not taking the entire node and replacing it. We just want the correct node that has to be replaced with the node to be deleted, right? So for that, what I do is I just simply write a function. Uh, like d is equal to find replace. You can give any name, okay? I'm just giving a name of, from the right side, I'm going to find the replacement, right? Or find replacement root dot right link. So now I need to write a logic to find the replacement for the right link. Sorry, for the root. So def now what is the logic? So actually I'm now to be able to is 70 and I pass the right link to find replacement. Okay, now the find replacement is having what? 80, right? That is 80's link, 80's address I'm having, but actually address assume that 80 is there. So what should I do? I should keep on traversing to the left side till I get the last node, right? So what is the condition? So here there's an iteration. Okay. So in this iteration, I want to reach 71. And what's the property of 71?
Left link is none.
Yeah, correct. So my condition would be while root dot left link not equal to none. Okay. Root is equal to root dot left link. Finally return root dot data. That's all. Understood? Any doubts on this? Yes. I'm iterating till root dot left link not equal to none. Okay, and then if every time I just move to the left side, okay, root equal to root dot left link. Once I reach none, it will come out of the loop, right? So I'll have root dot data that I will return. Fine. Yes or no?
Yes, sir.
Yes, sir.
Okay. So now I have D. So what should I do with D?
Root dot data equal to D.
Yeah. So I have to replace root dot data equal to D. Now this I have changed to 71. Next, what should I do?
Delete
I
70.
delete 71, right? So instead of writing any logic, I already have the code to delete, right? So I can simply call it recursively. Okay. So where should I replace the value that comes? Root dot right link is equal to bst dot delete of root dot right link, comma, what should I pass for key?
Root dot data.
Yeah, either root dot data or just D.
D.
That's all. Fine. See, that's it. 10 to 15 lines of code. Any doubts? So what you do is you can just make a note of this and then trace the code. Just take this tree and then try tracing the code. See, it's all link transfers only, right? So if the key is less than, for the next recursive call, key dot left will go. The key is greater than next recursive call, key dot right will go. Once I reach the data, I just check whether it's a leaf node or a single child node or a two children node and do the logic accordingly. Understood?
Yes, sir.
Yes, sir.
Okay, fine. So now let us go to the actual today's topic, which is graph. Okay, so graph is also a nonlinear data structure. Okay, like only difference between graph and a tree is that tree do not have any cyclic path. Okay, so definitely there will not be any cyclic path. Whereas graph can have a cyclic path. That is a cycle is possible. Okay, I'll show you example for a graph. Yeah. So can you see this is an example for a graph? And then like there are cycles, right? Okay, so 0 1 4 0. So that's a cycle. 0 1 3 4 0, another cycle. Like that, we have a lot of cycles here. So this kind of cycle is not there in a tree. Okay, and then one more thing is that tree follows an hierarchy, right? There's a root node, and then the next level, and then the next level, and finally the child node, leaf nodes, like that. It follows a hierarchy. Whereas in graph, it is not like that. Wherever you want to make it as a starting node, you can make it. So 0 can be a start node, 1 can be a start node, or wherever you want to make it as a destination node, you can make it. Okay. So this is a graph. So tree is also a graph, whereas graph is not a tree. All trees are graphs. Okay. Not all graphs are trees. Okay. So graphs like So this is cyclic graph. Okay, so that's a cycle. If a graph doesn't contain any cycle at all, that is called acyclic graph. Okay, and then there is one more variation. Um, graph. So you can see these graphs. So you have arrow marks, right? The previous graph there is no arrow mark. Here there is an arrow mark, which means that they are directed graphs. So which means from A I can go to B, whereas I cannot go to uh, A from B. So B to A there is no path. So this is directed. Okay, if you don't have arrow marks, that is bidirectional. So going to and forth is possible. Got this is the basic idea of graph. Now let us take this sample graph and then so I at the beginning itself I told you that all the data structures can be implemented using in the form of a list or a linked list, right? So first let us see how to represent this in a form of a list. Okay, so list means it will be in a form of a matrix. It means a list of list. Okay, so you'll be creating a matrix and that matrix will be like you have to visualize it as a list of list. I'll tell you after creating this. And the dimension of that matrix is going to be the number of nodes, comma, number of nodes. Okay. So here, these are called nodes or vertices, and this is called edge. Okay. Weight or edge. Okay. Fine. So here, how many nodes are there? 0, 1, 2, 3, 4, 5. So 5 nodes are there. So I need to construct a list which I mean a matrix of size 5 cross 5. Okay, so the values, the indices here represent the node numbers. So here what we have to do is we have to fill the distance. That's all. So we have the sample graph over here, and then we need to find whether there is a path between 0, so actually 0 and 0. So there are two ways in which representing the same nodes. Okay, 0 and 0, we can assume that there is no path at all. Okay, certain problems need to be assumed the path is 0, length is 0. Certain problems will need that the length is infinity. -1 means there is no path. Okay, 0 to 1. So is there a path between 0 to 1? Yes. So the value is 3. Okay. And then from 0 to 2, is there any path? There is no direct path. Okay. So here it is concerned only with the direct paths. If there are any alternate paths, did not worry about that. Okay. So 2 can be reached from 1 also, right? Okay. So, but we are not going to worry about that. If there is any direct path, we'll represent that inside the matrix. Else, we're just going to leave it as infinity. So -1 is represented as infinity. That which means there is no path. 0 to 3, 8. 0 to 4, 7. Okay. So one important thing that you can note is this is an undirected graph, right? For an undirected graph, the matrix will look symmetric. Okay. So symmetric means, see here 0, 1 will also be 3. Okay. 2, 0 will also be -1. 3, 0, 8. And then 4, 0, 7. Okay. You can simply fill whatever in the row you fill, the same thing can fill in the column also. That's why it is symmetric. Okay. So 1 to 1, there is no path. So minus 1. 1 to 2, there's a path. 1. 1 to 3, 4. 1 to 4, there is no path. So minus 1. So here I can simply fill 1, 4 and minus 1. And here it is minus 1. 2 to 3, is there any path? Yes, it is 2. 2 to 4, no direct path. So minus 1. Minus 1. 3 to 4, is there any path? Yes, 3. And this is minus 1. That's all. Okay, so this is how you will represent a graph in the form of a matrix. Okay, and this matrix is called distance matrix. Okay, where it contains all the distances. Okay, so we also have a common term called adjacency matrix. Okay, before that, let us know what is connectivity matrix. Connectivity matrix. So the name itself tells, right? If there is a connection, then mark it as it has connection. Else, you mark it as does not have connection. So for connection, we're going to denote the symbol 1, and no connection, we're going to denote it using the symbol 0. Okay. Again, it is going to be a 5 cross 5 matrix. Okay, and these cells are going to represent, if there is a connection, then it will be marked as 1. Okay, so from 0 to 1, that's a connection, so it will be marked as 1. 0 to 0, you are going to assume that there is no connection, so it will be marked as 0. 0 means no connection, 1 means that's connection. Okay, 0 to 2, no connection, so 0. Okay, the simple way of converting a distance matrix to a connectivity matrix is that wherever there are minus 1s, make it as 0. In all other places, make it as 1. That's all. Okay, so 1, 1. So 1, 0, 1, 1. 0, 1, 1, 0, 1, 1, 0. Okay, 1, 0, 1, 0, 0, 1, 1, 0. That's all. So this just gives the information whether the nodes, there is a connection between nodes or not. That's it. And this gives the information what is the distance between the nodes. Okay. And so this is a common term. This adjacency matrix sometimes it be used in for this as well for this. Actually, the adjacency means it has to be like okay, fine. So in both places it suits. Okay. So before going into the so this is how you will represent using a matrix. Okay. So what happens here is every row will be considered as a list. Okay. So there will be number of vertex. So number of vertex is something about here 5, right? So it will be a 5 cross 5 matrix, which means that there will be 5 lists with 5 elements in each list. Are you able to understand? There will be 5 lists, and then each list will contain 5 elements. So this is the first list, second list, third list, fourth list, and fifth list. I'm not going to give the implementation for this. You're going to try it by your own. So just need to create a list of list, and then you're going to keep on adding the elements. See, the input for the graph can be in 2 ways. One is they simply represent it as in this format. Okay, they give -1, 2, -1, 8 like that. The second way is they give the entire matrix itself as input. Okay, the second way of giving input is, so here they'll give the start node, end node, and the distance or weight. Okay, for example, they'll give 0, 1, 3. Okay, then 0, 3, 8. Sorry, then 0, 4, 7. Okay, so input can be in both the ways. Either they'll give the entire matrix like this, or they will give start node, end node, and weight. So if they give like this, what you have to do? You will create an empty list of list, and then the corresponding location. Okay, S of E, you will put weight. See this S and E, nothing but coordinates, right? Okay, 0, 1, you're going to put 3. 0, 3, you're going to put 8. 0, 4, you're going to mark it as 7.
But why you are giving as W weight? Because it was distance.
No, we can different names only we are giving. Either it can be considered as weight. This is also called as weight matrix, depending on the situation. Okay.
Okay.
W or D. Okay. See, it can also be a cost matrix. So we can name it whatever. Okay. So from traveling from Chennai to Bangalore, what is the cost? Okay. So like that, whatever is being put over here, we can just change the names. That's it. Okay. Now, yeah. So before, so we can see what are the applications of graph. So where all do we apply this graph concept? Can you tell a few examples?
Calculate the shortest path.
Calculate the shortest path. Okay. So, okay, fine. So you have a set of cities, and you want to find the between the start vertex and the end sorry, start city and the end city. You want to find the shortest path to which way you have to travel. Okay. So we have the Google map, right? So that is one of the applications. So any other applications where we cannot visualize graph at all, but graph is being used? So like for example, let us take Facebook itself. Okay. So you can see the friend suggestions and all, right? So how are they bringing the friend suggestions? Every
Each
user
one.
will be, yeah, every user will be considered as a node. They will find the weight between two users. Okay. So they'll apply a lot of parameters. Like the parameters would be like how many mutual friends you have. Okay, and then have you shared any common videos? Do you like common pictures? Okay, based on the location where you're staying. Okay, so
Okay.
like that they'll have a lot of parameters to suggest you that he might be a friend of you or she might be a friend of you, right? So there are a lot of applications like this. So you can create an irrigation system for a set of cities where to place the motor so that all the villages will get equal supply of water. Okay, in networking they use graphs. Okay, you can think about it. Lot of applications are there for graph. Wherever there is a possibility of distance calculation, you can just apply this graph concept. Okay, fine. Now let us see how to represent graph using linked list concept. Again, you're going to make use of list only here, not exactly a linked list, but it is a variable linked list. So now like we can see that there are a lot of minus ones over here, right? So are all these minus ones redundant? Do we need to store these minus ones and all? Not actually, right?
No, sir.
Okay. So we just need the information like 3, 8, 7, and to which node it is connected. That information alone is needed, right? So now what we do is instead of storing all the, instead of creating an n cross n matrix, so what we do is we just create a list of linked list. Okay, so I'll show you how it is done. So there are 5 nodes. So there are going to be 5 linked lists. I will mark it here. And here what I see this linked list, this is going to be a linked list. Okay, this is going to act like a head of a linked list. Here I'm not going to store the data. This is the head of the linked list. Now what will this linked list store is, it will store all the nodes that are connected to node 0. Okay, so how to find the nodes that are connected to node 0? Just iterate to the first list, that is 0th list. So wherever there is a non minus 1 value, those values are all corresponds to links to 0, right? So to 0, 1 is connected, 3 is connected, and 4 is connected. Understood? So what I do is I just create a node, okay, with 3 parameters. The first one would be to which node it is connected to. So 0 connected to 1, and then the weight of that node 3, and this would be the link of the next node. Okay, anyway, linked list means you should have a link to the next node, right? No. So what does this contain? 3 and 8. Okay. And here 4 and 7. And this will be none. And this would be pointing to this particular node. Okay. Mm. Okay, leave it. Able to understand, right? So this, there is a linked list over here, and this linked list corresponds to the data, whatever nodes are connected with 0. Likewise, we have the nodes which are connected to 1 in the second linked list, and then the third linked list will contain the nodes connected to 2. Like that we have. Any doubts in this? Yes. Able to follow this, right? Hello. No. Any doubts? If you have doubts, you can ask me. Not getting the idea? See, this is actually a linked list. Okay, so this linked list is having 2 datas. Okay, so one is the node to which 0 is connected, and then the weight of that node. Okay, 0 to 1, the weight is 3. So it comes over here. And here you have the node to which it is connected, which is 3, and then the weight of that uh, edge, right? Okay, weight of the edge, which is 8. Likewise, 4, 7. Any doubts in this?
Does so
Hmm.
does 13.238, sir, in the linked list?
Yes, yes, yes. This is a link to the next node.
Okay.
Okay, so can you tell me the link? Sorry, not link. Node, class node for this? So what all would be there? Yavdi?
0.
Hmm? No, for class node. What are the parameters of node? There are two data and then one link, right?
One link.
So what's the first data? To the vertex. Second data is the weight. The third is the link, which is equal to
None.
none. Okay, so sorry, self dot v is equal to v, self dot weight is equal to weight, w, self dot link is equal to link. So this is your node. Okay. Now you will write the append function. All those things would be here. Now for graph, okay, so we have a list of what? This list contains heads to the linked list, right? Self, comma. So if I, okay, so G is equal to empty list, comma, number of vertices. Okay. G, comma, number of vertices. So now what would be, like, what should I do is self dot G is equal to, I need to create a list of none. How many nuns? V number of nuns. Are you able to get it? I'm just creating this list where initially all the values are none. So all the heads are none only, right? Initially linked lists are empty, right? So just we are representing 5 linked lists which has none, head has none. That's all. And how many linked lists we are going to create? Which is equal to the number of vertices. That is why I put none into V. Any doubts on this?
No, sir.
Okay, so first we have created this. Then what you have to do is def convert matrix to list. So we'll be passing. So let me make it as capital G. Capital G for linked list representation, and let small g be for matrix representation. Okay. So G comma into just pass G. That's it. So just G, I'm going to convert it to capital G. Fine. So now what? So are you able to visualize this G? This G is nothing but small g is nothing but this entire matrix. So this matrix, how you will visualize? It is a list of list. Okay. So to access each and every element, use the index. Zeroth list, zeroth element. Okay. Zeroth list, first element. You'll get 3. Okay. How will you access 2 which is in the second list. Okay, second list, third element. So just use the index. G of 2 of 3 will give you this 2. As simple as that. Okay, so this is a matrix. It's a list of list. Fine. So now I need to iterate over this entire list matrix, right? So I need to iterate over this entire matrix, and then wherever there is a non minus 1 value, I have to append it to the corresponding linked list. So if it is over here, then I should append it to the first linked list, which is at next one. Okay. So for I in okay in G, okay, and then for okay, I need to store the index and all. So what I would do is I in range of length of G, then for J in range of length of G of I. Okay, or simply anyway, it's going to be square matrix. Instead of doing so much complications, you can just write it. You can just pass the number of vertices and you simply write V, range of V. Here also range of V. Fine. So now I'm going to iterate over this entire matrix. And wherever I find a non minus one value, I'm going to append it. Okay. So what's the condition? If G of I of J, so able to follow this, G of I of J, if it is not equal to minus 1, so what I would do is I just call the append function. And for this append function, I should pass the head of the corresponding list, right? So if I'm appending at 0th list, I should pass this particular value. So how to access this particular value? It's nothing but
Self dot capital G
capital G of
of I.
I. That's all. Okay. And then along with that, I need to pass two data. Okay. So in the node, you have two data, right? Vertex and W. So in place of vertex, what should I pass? To which node it is connected? How will I know that? It is connected to the
I
ith node.
yeah.
Okay. It is connected to the ith node. And then what is the weight? I need to pass 3 also. This 3. So how to find this weight? Sorry, not I. This J. Okay. It's connected to the jth node. And then, so what should I pass in place of weight?
G
This
of
value.
I
Yeah.
G
Small
of
g of
IJ.
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 That's all. So this is your normal append function. Okay, so whatever you have done for linked list append, the same append function, you can write it over here. That's it. So this is your conversion.
Shouldn't we use self for G also? For
Yeah,
G
we
of
have to use self. No, I'm giving an overall idea. It's not the
oh,
exact code. You have to write the append function also. So append function, you can write it, right? So same append function you're going to write. Instead of one data, we'll pass two data. That's it. Okay. Any doubts? Just make a note of it and try to like work it out and see. You'll understand. So just fill the append code and then you can run the code. You will get the output. Okay. And then now, like we need to know which is more advantage. Like whether to have it as a matrix itself or after converting it to list and storing it, is that more advantageous? Matrix is better or list is better? And I needed justification also. Why? Any idea about this? Can you think and tell me? Okay, I'll give you a scenario. Suppose there are 100 cities. Okay, suppose there are 100 cities, and among those 100 cities, suppose there are like 200 connections are there. Okay, so 200 connections are there among those 100 cities. Now, like if you represent it as a list of list, how many data would be there? I'll repeat the question. There are 100 cities. We're going to represent it as a graph. Okay, visualize 100 cities as a graph, and then there are 200 connections between those 100 cities. If that is the case, then how many data would be there, like in a list of list? -1 is also data. Okay, connection weight is also data. So totally, how many data would be there?
So 100
Uh,
into 200?
10 power 4.
Why 100 into 100? Sorry, why 100
100
into 200? 10
was
power 4 is correct. It is 100 into 100. It is just the matrix size. So
okay.
100 cities are there. Okay. So the matrix size would be 100 into 100, 100 cross 100.
Okay, okay.
Okay. So that'll be totally 10,000 data. Okay. Irrespective of number of connections. Even if there are 9,000 connections also, there are going to be 10,000 data. Fine. If it's a list. Okay. So in so if it is a linked list format, so how much data would be there? Assume it is a bidirectional graph. It means to and forth we can travel. You can go from city A to city B as well as from city B to city A. Okay, bidirectional graph. So how many data would be there? Okay, so what would be the
Uh,
size of this array or
100.
list? Okay, this is 100. And so each node will contain two data, right? It's like this. How many nodes would be there? Like this, how many nodes would be there? Every node represents a connection, right?
Mm.
So how many nodes would be there?
200.
200 connections are there, but actually there will be 400 nodes.
Double, yes.
Okay,
Data
because
in
to
the
and
lake.
forth, to and forth. Okay, from A to B, there's a path, means from B to A also there's a path. So that also has to be stored. So there'll be totally 400 nodes, and each node will have two data. So 800
Mm. 800.
data would be there, and there's a link as well, right? Actually, three into
Okay.
400, which is 1200.
1200.
So 1200 data would be there totally,
Mm.
and then plus this 100 for storing the head values. Okay, total how much?
1300.
1300. Whereas using the matrix, we had
10 to the power 4.
yeah, we had 10,000 data. Okay, so if you represent it as a list, we need only this much amount of memory. Whereas here we need 10,000 amount of memory. Okay, so this is like one part of the logic. Okay, so if we consider another type of graph where it is completely connected, so there is a graph called complete graph. What do you mean by complete graph? What do you think would be a complete graph?
There will be no -1.
No, what is a complete graph? So you're talking about the matrix, but what would be a complete graph? Okay, complete graph is nothing but
Each
every node is connected with each other nodes, every other node. Okay. Understood? Every node is connected with every other node. That is called a complete graph. In that case, how many connections would be there for 100 cities?
Ten power
Yes.
4.
Yeah. Okay, 10 power 4 minus 100 because 0 to 0, if you're considering no connections. Okay, then that'll be totally 9900 connections. Able to follow?
Yes, sir.
Okay. So totally that'll be 9900 connections. If there are 9900 connections, how many links would be there? I mean, how many nodes would be there? 9900 nodes would be there, right? See, the connections would be by 2, this by 2. I mean, the entries here would be 9900 and rest all would be minus ones. The diagonal part will be minus 1, okay? So diagonal part will be minus 1. There'll be 100 diagonal values, right? So the diagonal part would be minus 1. So that's why minus 100. So totally there will be 9900 nodes. So into 3 would be the total number of data. Are you able to follow? So in that case, this is not suitable, right? So depending upon the scenario, it changes. So if it is a sparse graph, okay, then we'll go for list implementation. If it is a complete graph or near complete graph, then we go for matrix implementation. Understood? Okay. Fine. So I think it is enough for today. So till we have the graph traversal. So two types of traversals are there: depth first traversal and breadth first traversal. So we can see it in the next class. Okay. So now today you have to understand the deletion part of tree as well as the representation of graph. Okay. Fine.
Okay, sir.
Okay. So thank you all. We can meet in the next class.
Thank you, sir.
Thank you, sir.
Thank you.